Starting one of our longer sections on mixed models. So we got through the GE where we're only concentrating on estimating the mean model. And again, we don't try to model the correlation structure. We just guess the working one to help the estimation process when it matters. We've talked about how that's complicated. Now we're going to mixed models where we're going to estimate the whole likelihood. So it's like, just to remind you, like G, you get the results back. You can't simulate from what you know from G. It just gives you back the mean. It doesn't give you back the error distribution. This will give you back everything. I mean, again, whether it works well depends on whether the model's well specified, but it's a full maximum likelihood. So you're not using an estimating equation approach where you use maximum likelihood, but just to sort of motivate an estimating equation that is consistent in more general terms than if the likelihood happens to be perfectly specified, only for the mean, to something which is more pure maximum likelihood. Sorry, I don't know why it's doing that. The one thing I wanted to mention is that I was going to post today the final project instructions. And so it's going to be, project of your choosing, just to give you some background. Teams of 1 to 3, no bigger than 3, no less than 1. And you can choose a variety of things, which I'll tell you about. You can, if you have data that you're working on, that's longitudinal. That's usually the best choice, since you can kill two birds with one stone, or you can do some other public data set that you want to analyze it using approaches that we learned in here. You can concentrate more on the methodology, like a specific methodology we didn't talk too much about, for instance. And there's lots of those that are related to longitudinal. And for instance, more details on like latent mixture models, things like that. It'll be roughly 15-minute talks of your group. So going to be in class during RRR week. We may only need one class, depending on how many teams are formed, but we may need two to get through it. So, but we'll know that later. So I'll send out that today, and you can start forming your groups and thinking about what you want to do. And then if you like need an idea, or you want to maybe ask about an existing data set, welcome to talk to Nolan and myself about that too. Okay. So mixed models. They have lots of different names. The mixed model is the most general term. It just means it's a mix of, it's a regression model of some kind that's a mix of so-called fixed effects, things you measure, and latent variables, usually some kind of error term that you specify. But in certain specific forms, they'll have different names. Random effects models is one. That's just an example. Random coefficients, another example. Multi-level models or hierarchical models. All these are different classes. And depending on which type of thing you're fitting, they may have slightly different ways of estimating the coefficients. If you take a class on hierarchical models, because they're hard to identify often, it's hard to estimate all those variance terms. The estimates themselves are fairly collinear, so people will use things like Bayes overprint to try to make them easier to identify. So you can see a lot of different variations depending on how hard it is to estimate the underlying model. And we're going to start with linear, but it's basically a generalized linear model form. So you can have mixed models that are linear, mixed models that are logistic, mixed models that are Poisson, the typical GLMs you can use. All right, went over this. Again, what's being mixed is there's so-called fixed effects, which are like, you can think of those are effects where you observed every category in your sample population that's in the target population. So if I'm looking like levels of a drug, or I'm looking at things like gender, socioeconomic status, things like that. We're not taking a random sample of those units, but they're measured, and the fixed effect means there's some effect that applies to the whole population. Then there's a random effect, which applies more to the specific unit. So it could be everyone has a different intercept, or everyone has a different slope. And you're not collecting everybody in the population, but some subpopulation in your sample, and you're only getting a sample of those various levels. And there can be variation. Sometimes whether you call it fixed or random depends sometimes on the practicalities of it. Like, you may collect the zip codes, and you'd like to adjust for zip code itself, but if you have 1,000 of them, you don't want to have to estimate 999 dummy variables. So sometimes people treat things as random for the ease of fitting a model, when in essence they're not really. You've collected data from every zip code. So you'll see some, there's the ideal situation, but then there's some ways it's used more practicality, because there's so many different levels. Even though you have every level in the target population of interest, it's just more convenient, or even possible, to estimate the effects of interest by treating them as random. So I guess the first question I could ask is a treatment. Let's say I talk about repeated measures on an individual, for instance. Is a treatment effect a fixed or a random? What would it be?
Fixed.
Can be all fixed, right? I could have the average population effect, right? That would be a fixed effect. I could have everyone have their own treatment effect. So it could be both. Yeah, so a lot of these things can be both. They can be both in your model as a fixed and a random effect. You can have both. So you have a model where it just means that the coefficient, that's the fixed effect part, changes. It has a different interpretation. It's no longer the effect, it's the average effect, right? And that depends on your model. So it can be both. And again, sometimes it can be subtle. Usually it's not. I mean, for the most part, we're talking longitudinal. You have people. We assume those are randomly drawn from bigger population. We rarely do fixed population inference, although that's possible. That is, we don't treat the people as random. We get the inference as if we're going to go back and collect the same people, but go through the process by which we assign treatment, et cetera, and that part's random, but the people aren't random. That's a fixed population, sample population. Not commonly used, but you'll hear that sometimes. Generally, we have measurements on people, and the people are treated as random, a random subset. So for instance, if I think of every person in the population has an intercept, I don't get them all. I only get a sample of those intercepts. It's basically a random sample. There's a lot of motivations these are very popular methods across many different disciplines, because they have a nice intuitive feel. Like you build a model where you say, okay, I believe these people should vary in this parameter and not this parameter, and so you can sort of work your intuition directly into building a model that reflects what you think the sources of variability are come in. So, it's often reasonable to think, okay, well, there may be an average treatment effect, but I don't believe everybody that I assign treatment to versus control is going to have the same effect. So it may be natural to include, let's say, a random treatment effect, for instance. The other thing that can also be relevant, not always relevant, depends on the context, but if I'm predicting, I'm going to do a prediction on a population, let's say zip code, and I'm going to predict their accident rate next year or something. And I treat the zip code as a random thing, I can get predictions which take into account the actual units random things. After you fit these models, you can get the estimate of the random intercept per subject, let's say, or per zip code. And those can be used in prediction, but only if you're predicting on the same zip codes that are in your data. Otherwise, you don't have that estimate. But so it's often used in this context for spatial data. Some version of this often is used in spatial data, where you have the spatial units are considered random draws, and you can get better jobs, let's say, estimating some surface of disease prevalence or something like that. And the other thing that's nice about it is, as I said before, you get the entire data generated distribution. I mean, again, we're always conditionally on covariates. We never estimate the distribution of covariates. We don't have to in order to estimate the conditional distribution of the outcome of covariates. So that's always, we don't have to estimate it. So that's not usually what the likelihood specifies. It's not relevant to the parts of the likelihood we care about, which are like coefficients and maybe variance terms. It can use the virtues of having, it's great to have a likelihood. You have ways of measuring the relative fit. There's lots of theory that tells you in the class of models that you're fitting in likelihood, the maximum likelihood is an optimal estimator. So there's theory to sort of justify its use. Lots of theory in deriving inference for the coefficient estimates, how you get standard errors, et cetera. And again, if I want to, if an example that I come again is you have a study people have done, which is like a repeated measure study, and they want to design a new one from it for, let's say, a trial or something. I can use estimates of the model on the current one to sort of simulate what would be my power if I had this many people or this many subgroups, and it allows you to simulate, right? Which again, GE does not. You can use the results of GE and add other information that you'd have to make up or estimate separately to get a simulation, but generally you don't have every component of the likelihood to simulate. I can get the mean of y given x, but I can't simulate y given x because I don't have any estimate of the error distribution. So we've seen this before, so we'll just look at the first simple example. This is a very simple example. We would normally call this the fixed effects. It's just the mean, right? We don't have any coefficients here. We just have outcomes. So we just have a random sample of individuals and then repeated outcomes on individuals. And then we might say, okay, well, I believe everyone's mean is different in the population. They don't have the same mean in their repeated measures, right? So I'm taking blood pressure measurements on different people, and I'm taking 100 measurements per person. I believe that there's a grand mean, mu, but also everyone has their own mean. So like E of Yij, given alpha I, given if I knew that person, would be mu plus alpha I, right? While the mean of Y over all alpha I is mu. So that's just, again, you're modeling that variability, which you think might be a natural source of variability, the fact that not everyone has the same exact blood pressure, a mean blood pressure. So you think of mu plus alpha I as the long-running mean if I took a infinite number of blood pressures on a single subject, right? This will just always be the case. We always term the error terms will have mean zero. These random things will have mean zero. Otherwise, I can't identify mu if alpha is equal to, the mean of alpha is equal to gamma, then the mean becomes u plus gamma. So you can't, in order to identify the parameters of models, you have to assume the error terms are zero. It doesn't really change the model that much. And then you have to specify other things about them, like the variance. Again, you don't specify that. That's another parameter you get. So in this case, and then this will always be the case. You could generalize this when it's possible to identify the parameters, but the covariance, this is the covariance. They both have mean zero, so I can represent the covariance as just the mean of one times the other of the random things measured at different levels will assume are independent. That's also for identifiability. If you don't assume they're independent, it can be impossible to, there can be an infinite number of solutions that fit the data just as well. That's what non-identifiability means, that the data won't lead to a single estimate. In this case, the fixed effect is really mu. The random stuff is always the stuff that has a subscript I or a subscript EI, IJ I mean. So it's like the alpha I, you can think of the EIJ error term, which will always add at the end of a linear model, is also the random stuff. So we've got the fixed stuff and the random stuff. And again, what's the interpretation of mu? It's not the mean of every, it's the overall mean of all individuals, right, in the population. And again, the mean of a person, if I knew that person alpha I, would be mu plus alpha I. Now this, we've gone over this before, but just to remind you, this has a particular implied model for the variance covariance of an outcome in this model. And it looks like this. If I worked out the correlation of observations on the same subject, it would be equal to this. It's the sigma squared alpha over sigma squared alpha plus sigma squared E. The total, the variance of every observation are these, they're independent, right? So the variance of alpha I plus EIJ is the variance of one plus the variance of the other. I assume they're independent, right? That's where I can use that independence assumption here. So I know the variance is just the sum of the two variances. And then the covariance will be sigma square alpha. So some of these things, like a simple random effects model, has this, the covariance is always the random effects that an observation shares. So every mu I, whether it's mu I1, mu I2, mu I3, they'll all have the same alpha I in it. So, but they'll have different EIJs because that just varies by the observation number J. So they both, all observations on a person share alpha I, and therefore the covariance is sigma squared alpha. I mean, you can also just do the math to show it, but that's kind of a general rule people often use, that the covariance is the sum of the variances of the random stuff each observation shares, whatever two observations you're comparing. And of course, if I look at two different people, they don't share an alpha I, so their covariance will be 0, right? Anyway, there's always generalizations of these methods, but typically for fitting mixed model, you don't specify explicitly the variance covariance model. You would do it implicitly by how you add the random stuff. It will imply a certain one, a variance covariance model. Now, there are ways to generalize it where you say, well, I believe it looks like this in terms of, they share this alpha I, but maybe I have the EIJ be autoregressive. Like, you can generalize these things to more complicated structures by, really, it's always assuming something on the error term, on the last term, that has some other form, kind of like we assumed with the working models in GE, but typically what you do is you specify the random part in there, you just have the EIJ as random independent errors, and that model will imply a certain variance covariance structure. And that's what's used in the estimation and in the inference. This is a more interesting version of the model, which is I've got this beta 0I, so I assume the intercept changes by the person. I also have a beta 1, this should be a capital X. The beta 1 changes, so it implies that everyone has a different intercept and everyone has a different slope. Again, it's the same intercept and slope for all the measurements on the person I, but it changes when you go from one person to the next person. Again, you don't always have to specify these assumptions. They're typically just assumed implicitly when you run the packages in R. But again, they'll assume all the error terms that mean 0. That'll always be the case. And then they'll have some variance that they'll estimate. And then covariances. Now again, these are assumed. These are covariance of random things measured at different levels. One's at level I and one's at EIJ. So we assume if they're measured at different levels. And this isn't necessarily true. It's just what's required to identify the estimates of the variance terms. You have 0. If you're measured at the same level, you can make an assumption that they're uncorrelated. That's weird. You would just assume arbitrary correlation or covariance between any two random effects measured at the same level. If their slopes, I mean, that makes perfect sense that if your intercept's higher, your slopes, and most people are going down, if your intercept's higher, you're probably going to have a steeper slope, and if it's lower, you're going to have a shallower slope. So it makes sense that the slopes and intercepts will be correlated within the same person. It'd be weird to assume 0 in that case. You do these because you have to. And here's usually the default. Again, if I have a beta 2i, I assume correlation between all the beta 0i, beta 1i, beta 2i. In this case, what are the fixed things? Well, we call this a fixed effect and this a fixed effect. I mean, it's better just to think of their interpretation. Beta 1 would be not the slope, it would be the average slope, right? The average across all the people in the population, their average slope would be beta 1. And then the random stuff, the random effects are, yeah, people have random, I'll choose different color here. There's random intercept, and there's a random slope, and always the error term. So combination of things that sort of capture where you think the variability could come from. We'll talk in the future, relatively near future, about how to try a bunch of different these types of models and use model fit statistics to choose between them. Because oftentimes it's done very empirically. Like once I have more covariates, and if I have time dependent things, covariates, I can always add a random effect. But after you get too many, it's very hard to identify the various variance terms. They tend to be highly correlated, the estimates of them. So if I add more and more of them, I can't distinguish the variance to the intercept from the slope, and the likelihood levels off is what you can think of it. So think of the maximum likelihood for some parameter goes up and just stays flat, and so there's no single value anymore that gives you an optimal answer. That ends up happening. So part of it's kind of empirical. You try it and it says, usually gets back a nonsense answer, or says can't identify it, and you try something that's smaller. Basically, it's hard to predict necessarily. Like we'll talk about situations where if I added a beta 1I, I wouldn't be able to identify the variance of beta 1I. There's some situations where that happens, and you can determine that a priori. But a lot of times you can't really tell. It's complicated. It depends on the joint distribution of the covariates and how they're related to the outcome, et cetera. So sometimes you just have to try it and see. Again, I don't care about the math part of this at all. Nothing I expect you to remember. It's just that when it's going to build its variance covariance, which it needs to do, just like GE, when it gets its estimate, it's going to be weighted regression. And we'll see that in a sec. And that weight's going to be a function of the estimate of the variance covariance matrix of the outcome. And whatever you choose is going to affect what that looks like in terms of your random stuff. So in this case, you can see by having this random intercept, let's just ignore that, and you can just ignore this. Just look at this one. You can see that the variance of Yij, and this should really, technically, I use a shortcut, but it should be Xij. It's the conditional variance. We don't integrate out the variance caused by Xij. It's always conditional variance on that. That it's a function of X now. Right? So it's not constant anymore. And that means that you now have a variance for the outcome, which is a function of probably the predicted value for the outcome. So when Xij is related to the mean, it'll be a function also of Xij probably as well. So anyway, you get heterogeneous variance estimates. Not always. We didn't in the simple model before, but we do here. And that's because we have this beta 1I times Xij, and that's going to take the variance of that term. It means that Xij is going to be part of that variance calculation. So it allows you to have a rich class of variance covariance models where, again, you're not specifying directly. I don't put this in the equation. I just define that original model, and it automatically does this behind the scenes. It figures out what the variance should be given your estimates of the variance terms and the covariance terms. Again, that's easy. Basically, anytime you have a random coefficient, not the random intercept, but a random coefficient, like the effect of this is different for different units in your population, you'll get this as a consequence that the variance will no longer be constant across observations anymore, because it'll be a function of whatever Xij you're multiplying it by. So if I just look at the likelihood, in order to find the likelihood, I have to define not just the variance, I have to define the distribution of these terms. And all the error terms are always going to be assumed to be normal. These are nothing you can estimate directly with the data, right? You get some sense of them maybe, but you can't estimate it directly with data because we don't observe it. Right? So That's the thing about latent variable models. They make pretty big assumptions that are not testable, right? So, I mean, it's always a risk that you're fitting a model that may be giving you inferences that are based on more of the model than the truth. That's always a risk in statistics when you start making assumptions that are non-testable. If I look at, this is just you can think of as the likelihood of just one observation. Conditional on alpha I. And again, I didn't put that here, but this is the model. It says alpha I. It's that model we looked at before. So if we look at the likelihood of just one observation, conditional on alpha I, it's going to be normal, right? Because that means the only thing that varies in this model is the EIJ, right? So it really, if I do that, it's just this is just the EIJ up here, right? It's the same, just y minus the alpha I minus the mu. And of course, I standardize it by the variance of that term. It's going to be, this is a normal, standard normal 0, 1 density. This, well, it's not really popularly, it's a density. I'm not going to get into the distinction here, but it's is density of x in normal 0, 1. And again, just to give, so we're all on the same page. And if I knew, of course, if I knew alpha I and I knew mu, when you condition on something, you're pretending it's known. So I pretend it's known, then the only variability in Yij is just the function of the error term. So it's just the standardized density. It's a density of that standardized residual where I divide by its standard deviation. And because all the alpha i's are independent, if I look at the whole vector of observations on the subject, so again, this is yi1, yi2, it's a whole vector, I can represent that as a product because they're all independent now. EIJs are all independent of each other. So that's specified. You don't specify that directly, it's always assumed the EIJs, unless you have some specialized correlation structure, are always independent. So if they're independent, the probability of the density of one of a vector of them is just the density of 1 times the density of the second, third, fourth, up to the final observation. So it's just the sum of these densities, and that would be the density if I knew what alpha I is. So then you're at this, then the question is, I don't know alpha I. So whenever you don't know a latent variable, I get the true likelihood. The likelihood can't be a function of unknown random variables. You have to integrate out over the distribution of those random variables to get something that's, in this case, was just the density of yi itself, right? So I have to integrate out over the density of the alpha. Again, the alpha are normal, and if I divide by the standard deviation of alpha, it's standard normal as well. So I can represent its distribution as a standard normal. And therefore, when I get this is the likelihood, this is just what I observe. I just observe a vector of observations on a single person, yi in this case. It's just that conditional distribution given alpha integrated over all possible alphas. So, it's what you would think. You get, it's a function of unknown thing. I need it to be a function of only what I observe. So I have it now in this form of the density of alpha I of yi and alpha. In order to get just yi, I have to integrate out the alpha. And that's all I'm doing here. So this is the standard form of mixed model or any latent variable model. is this thing right here. You first define that you want it to be a product of stuff, so I condition on what I need to do to make the density of a vector of things to be the product of their densities. And that's true if I say I pretend like I know alpha I, and then I have to integrate out alpha I because I don't really know it to get the marginal distribution of what I observe, the data, that is the defined as the likelihood. So this is how you build your likelihoods. Of course, I can do that now for every vector of outcomes on every person, and then the likelihood is just the product of all those things. So that's how you build the likelihood. And again, it has likelihood as, unknowns are the coefficients. In this case, it's just a mu. We have one coefficient, essentially, a mean. And the likelihood is also a function of the variance terms, the variance of E and the variance of alpha. So those are the things it has to solve the likelihood for. Anyway, you never have to do this directly. This is all done by the software, but this is what it's doing. There is a complication, which I may come back to, is there's something called restricted maximum likelihood estimation, which is what's sort of the default when you do these mixed models, and it tries to get rid of some bias to the fact that when it estimates the variance, you account for the fact that you're also estimating the mean. Full maximum likelihood ignores that, but reduced maximum likelihood tries to get rid of that little bias. I look at that important of a topic. It's technical. Absolutely, it doesn't matter. So I tend not to teach it too much, but just you'll see that term if you read things, and some books spend a fair amount of time on reduced maximum likelihood. How do you get it where you account for the fact that you're simultaneously estimating the mean and the variance to avoid that variance. So an example of a restricted maximum likelihood estimate of variance is the sample variance, right? In the maximum likelihood estimate of the variance, if I assume y, a random variable just cross-sectionally measured, so independent across subjects, no repeated measures, the maximum likelihood version, I'll put squared hat MLE is 1 over m equals 1 to m minus y bar squared, right? But this sample variance, which accounts for this has a little bias. If I take the expectation of this quantity, I don't get exactly back sigma squared. I get sigma squared plus a little something. The sample variance is one of these forms of, think of it as a restricted maximum likelihood. It's 1 over m minus 1. yi minus y bar squared. And this you can think of as R MLE. So you can use the same principles in general for a restricted maximum likelihood. You can derive the sample variance. That's not the way it's really derived. It's really derived by saying, I know the variance is biased, how do I make it unbiased? So you can see you just divide by n minus 1 and not n. But again, you can see very small differences between these two, not really that important typically. And so I don't spend a huge amount of time going over this difference. Because it can be in math, lots of matrix algebra, and I don't find it very useful. But just note that that's kind of the default, is they try to get rid of this finite sample bias in the estimates of the variance terms by using restricted. So again, if this is my x, and here's my phi of x, it looks like this. And if I call this x0, that right there is x0, right? It's symmetric around 0. In this case, it's 0. Is the mean. It's just a standard normal. So anyway, just the density from the standard normal, which is how you define the likelihood when you're fitting linear models, because you're going to have to assume something about the error distribution. So normal is the typical assumption. So the estimation, we talked about this in GE, is very similar in some sense. So it turns out the maximum likelihood estimate, if I try to solve that likelihood in the linear case with these random effects, it turns out it looks just like this. So it has this analytic form where has a weight matrix, right? So it's like weighted least squares. And you weight by the inverse of the variance. So the estimate of the variance covariance matrix that we always were talking about earlier. It gets, and again, it gets it by 1, getting the form of it by using the model, and then estimating those parameters, plugging them in, and then running the regression with these current estimates, gets the residuals, gets new estimates of the variance terms, and does it till it converges. So it's weighted maximum likelihood, where the weight is the inverse of this variance covariance matrix of all the observations in your data. So all repeated observations on the subject. And of course, they'll have certain form depending on what your model is. So very much like the linear case in GE, where W is now a function of the mean model and whatever arbitrary correlation you're going to assume, and the working correlation. This is very similar. It turns out sometimes it'll be identical to what you would get for GE. So if I assume a simple random intercept model, that implies exchangeable working correlation. That's what it will imply. And so when it does that, it'll be very much like estimates and inference from a linear GE with working correlation as exchangeable, as you would get if I did a mixed model, but I did a simple random intercept model. So there's sometimes where there's some equivalence between those kind of fits. There will be a difference between the robust estimate of the variance, right, and the, tell me why. That's a good midterm question. That's too late for that. Why will the robust estimate of the variance for GE, for exchangeable, be different than if I get the estimate of the standard error from Finney mixed model, which implies the same exchangeable working correlation, right? Why will the robust, how could the robust be different in the GE case than the naive? First, let me ask a better question, or more, less confusing question. You get the inference back from mixed models is always naive. You can alter that. There are ways, you can bootstrap, do other things to make it robust, but typically default's naive, meaning it's going to give you back your estimate of standard error, assuming whatever variance model is implied by your random effects model is, or mixed model is true, right? So it's always naive, right? So I'm saying that if I fit a simple random effects model in a linear model, and I get the naive standard error, it'll be the same as the standard error returned by mixed model, assuming a simple random intercept. They both have the exact same implication for the working correlation. And of course, the GE naive, we don't use it, but it assumes that you guessed exchangeable is correct. So if I look then at the robust and it's not the same as the naive, what does that imply about what? For 25 cents, for $5, for an A+.
This is GE, you're saying? Like, how does, there's a difference in naive and robust standard errors, what does that say? Is that what you're saying?
Yeah, there's a difference between the robust standard error and naive in that context, where it means that two things. One, it means the working correlation assumption was not good, right? Because they're different. And secondly, it means the mixed model will also be biased, because you can tell their inference will be biased because it uses the naive, and the naive assumes the same as the GE. So it just tells you if you're fitting something that a mixed model that gives you something equivalent to GE, just go ahead and fit the GE in this case, just to make sure. But again, there is this philosophical thing where we should always report robust standard errors, and generally that is not the default. And you could always, no matter what I'm fitting, mixed model or GE, I can always at the end get robust standard errors, but it's not the default. It's not, you have to do that yourself. So just keep that in mind. So this just goes over, this essentially that's a whole naive versus robust standard error stuff again. What we talked about with GE, it applies here, except for it always defaults to the naive. And again, what it does is you fit up. You start always fitting just a simple linear regression model with the weight matrix, no weight matrix. You get your residuals. That's used to get your maximum likelihood estimates of the sigma terms you need. That builds your variance covariance model. Then you refit the model now with weighted regression. Do the same thing until it converges. So estimates of both your variance terms and your coefficients don't change anymore. They converge to some set of numbers. So that's the way it works. That's why there's even though it's linear, there'll be iterations sometimes because it takes more than one iteration to converge. If you assume the model is right in the mixed model case and the turns out GE case, then your resulting variance will look like this. So things cancel. Remember I had the sandwich estimator before, or it's the X transpose, blah, blah, blah. And then you had this in the middle of it. It was the variance of the whole vector of outcomes. Things cancel out, just so we showed in the simple linear case, and you get this thing right here. So in other words, to get the variance estimates of the coefficient estimates where it derives the standard errors from, it uses this formula in the linear case, and it plugs in an estimate of the variance covariance you got by assuming it was true, right? So it's naive. And therefore, if that's a bad estimate, you won't get good inference. You get biased standard errors. Okay, I just want to point out, I gave you guys a bunch of stuff yesterday in that subdirectory under our lectures. It has this lecture. It also has the next lecture, which comes from an RMD file, markdown file, so you have the code and stuff in it. This overlaps with that one, so I'm going to go over stuff that's at the beginning of that RMD file, just so you don't get confused, where I paste in the stuff here. I don't usually do that, but I messed up. So this is stuff you can run your code yourself within the RMD file and get the same results. So I'm going to go over these. We did these examples with GE. Remember we compared them, where we compared fitting exchangeable, looked at naive and robust, and independence and naive and robust. And then we looked at different situations. So it's the exact same thing where we're taking simplified forms of that CD4 count data. And first we're having a time independent covariate, right? Which is age. So it doesn't change. We only have 2 measurements per person. All this stays the same. So here's my model. Again, this is binary. Say right, 1 if you're over 40. These are the underlying assumptions of the model. Again, I don't typically have to specify these. They're just implicit if I define this model with my code. And then I'm fitting that. So as opposed to a GE fit, I'm fitting a mixed model with a random intercept. Okay. We saw this one before. So again, if you remember this one, exchangeable was the same. Robust and naive, so exchangeable looked like a good fit. Again, it didn't affect the robust inference at all because there's no change in the estimation at all if you have independence versus exchangeable and you have 2 observations per person and it's balanced. We went over that. Now I'm just fitting this. So it's the LMER. For linear, it's LMER. There's other packages, but this is the one we focus on. And this is the way you put your outcome, your Yij, you put your Xij, and then you add your beta 0I here, where you put 1 means intercept, and the ID says what level does it differ, right? I could have hierarchical levels. I may want a different intercept if I have some other level of the hierarchy, like household, individual, repeated measurements. So that's how I specify this model. Again, this model is Yij, beta 0 plus beta 0I plus beta 1 Xij plus Eij, right? That was my model. This is always defaults, it puts an error term that's in, the Eijs are all D, normal, 0, sigma squared E, right? So they're independent. I always assume that error is independent. So it's not, it's independent even if it's on the same person. So the correlation doesn't come from the error terms, it comes from this beta 0I term of observation of the same person. And what do we get? We get something here and here that looks a lot like this, right? Because it's exactly the same. It's essentially the exact same fit and the same inference as naive. It turns out the naive and the robust are about equal for the exchangeable because it's a good fit to the data. And so we get something very similar there. And if I did robust, I'd also get about 19.2 because, again, because we have evidence that the exchangeable works pretty well here. You also get these things back. So you get estimates. Well, these are the standard deviations. These are the variances of these terms. So if I look at this, there's a fair amount of difference in the intercept, right? That's 157 in CD4 count units is pretty big. So people start at very different parts of at time 0. Time 0 is a meaningful time here. That's the time they initiated treatment. Well, actually, that's not it. That's just the mean. That's just the variation in intercept when your Xij is 0. That's all it is. So if your age is young. So a fair amount of variability there, more so than the Eij. Now again, we're not interpreting these too much now, but what would be my correlation estimate here? Correlation would be 24883 divided by 24883 plus 5095. So the correlation appears pretty high for those repeated measures, right? In this case, equals high. Anyway, practical circumstances, I don't see any really, unless you need estimates, because you don't get estimates of the variance of beta 0I when you fit a GE. If that's not of interest in itself, with GE seems like you would just, for linear models, often a good way to go. You don't get a lot of separate information in the linear case unless you have complicated hierarchical models where you're not just having a single random intercept, but maybe they're hierarchical intercepts or you have random coefficients. Okay, now we'll try this term where we'll add this random slope. So now we're saying everyone has their own slope of the association of age and CD4 count. Before, everyone we assumed had the same slope, but now we're adding this. Again, these are just all the assumptions that the program makes behind the scenes. And again, we'll have an arbitrary covariance between those two. So we'll assume they could be related. As your intercept goes up, your slope goes down, or vice versa. This won't work. It'll say it's not identifiable. You know why? Think about it. It's trying to get estimates how the association of age differs from person to person. But how many ages do we get per person? 1. It's a baseline covariate. It doesn't change. So you need to have some variation in order to get a random slope, right? Because you have to think about it. If I couldn't, in theory, estimate a slope, even just using 2 points per person, then how is it going to get the variability estimate of those slopes? It can't, right? So it won't work. So this is not, it turns out because of quirks of math, this isn't necessarily true when we do logistic regression. But in linear regression, you can't get random slopes, coefficients, on time invariant covariates. It won't work. They're not identifiable, right? Because you need to have variation in that covariate within the person to get its estimate. And therefore, then you can get the variance of those estimates across the subjects. So basically, you have to have variability, time variable covariates in order to get random coefficients on them. That's just a good thing to remember. And even if you do have variation, you have to have enough. So even if I sometimes do have more than one measurement per person with different values of that, I may not, maybe I don't need just two, I need 3, 4, or 5 in order to do it. So again, it's hard to know for sure what will work ahead of time, but I know this would not work a priori. This is one of those situations where there, if it doesn't vary within a subject, you can't estimate the association at the subject level, which means I can't look at the variability of that estimation at the subject level. So not identifiable. All right, here's the other one we looked at. Now this is where you have that time-dependent covariate. So this one does change. It changes for everybody. So data is constructed so everyone has a low viral load count and a high viral load count. 2 observations per subject. Again, the covariate's binary. So I'm going to fit that simple random effects model again, and let's see what we get. This is what we got for GE. In this case, you remember the one thing we got here is the robust is much smaller than naive because in this case, ignoring that correlation on the same subject biases the standard error big, which can happen. I gave you a brief explanation of why that can happen last time. Again, it's balanced data, so exchangeable and independence won't change the estimate. And also, if you look at the robust versus naive for exchangeable, which is a better fit, again, in this case, it's pretty much the same. So we would expect if we're going to fit a random intercept, we're going to get something that looks like this. And that's what we get. It's not perfect. It's not exactly the same estimator, but it's pretty close. That's basically what we get. Now, again, we get our standard DV estimates of this. Again, it looks like a pretty high correlation because the correlation is 23820 over 23820 plus 8960. So a little less correlated for repeated observations on the same subject. But anyway, you get the bottom line. So it's a different way of specifying the same exact correlation structure exchangeable, but you're doing it through adding this random intercept, which implies exchangeable correlation, and therefore the naive for GE should be about the same that you get when you get the naive back from the mixed model, from the random intercept model. It's not guaranteed to be close to the robust. In this case, it is, so it implies it's a pretty good fit. Yeah?
So the interpretation of the estimate would be exactly the same between these two? Like
They're not, they're not exactly the same. Like,
Yeah.
It's not exactly the same.
So they're not
That's
like,
right. They're not going to be like the same to the third, fourth decimal, typically, the estimates.
but
they'll-
the interpretation of that.
exactly the same.
Yeah, yeah.
Exactly the same. We'll go over this in some more detail later, but the interpretation for linear, when you have, if you think of technically for a GE model, the interpretation is if what I get, if I regress the Yij versus the Xij, and I want to I want to get the average association in the population. The mixed model case, if you look technically, how do I get beta 1 alone in a random intercept model? It means I change Xij by 1, but I have to keep beta 0i fixed, right? So that means it's the change for 1 unit change in Xij, specifically for subject I. But also, if I take that and I take the average over all the i's, I still get the same number. So it has both a marginal and conditional interpretation in the linear case. That's not true in the logistic case. They don't have, the coefficients don't have that duality of interpretation, that you get something different in the GE than you do in the mixed. And again, it's just based on math. There's not a lot of intuition for it. But in this case, you can interpret this as this is the change within a person and the average change across people. Okay, we're doing the same thing we did last time. Again, we're just trying to add this one. Again, we only have 2 observations per person, and you're trying to essentially you're trying to look at the variation of slopes across people, but if they only have 2 observations, that's going to get close to non-identifiable, and in this case, that's true. can try it. It may be possible that it would work if I took this out. By default, if I put this in, you also can't identify it. If I had 3, I probably could identify it, right? If I had 3 observations, but just, that's what I'm saying. I not necessarily can guarantee that will be the case. I think in this case, you could a priori say that you need more than 2 observations to estimate a line with some variability. Yeah.
Is the criteria like for empirically when it's not identifiable? Like if you try to run this in the model, like it won't converge?
It doesn't
Or-
converge.
Okay, so just
It's
goes
empirical.
uniformly, Okay.
I mean, it's both empirical and you. I think in this case you have to have some idea of the error around the line in order to distinguish the error from the residual, from the error
Right.
from the variability in the lines. But you can't get there because you only have 2 points.
Yeah.
So it won't be able to distinguish the sigma squared e anymore from the sigma squared 0.
Okay.
So it still won't work here. If you have 3, I can start to do it because I now have the possibility to have some residual variability within the line
Right.
and the person that I can start separating out the residual error from the between subject error. So, again, depending how the design of the x's is, maybe it's still not quite enough and it won't work. That's empirical. Like I can't guarantee it.
Yeah. Okay.
This I think you can guarantee because there's no way to get, it's totally confounded. The between subject variability and the within subject is totally confounded if you only have 2 observations per person. I'm pretty sure.
So it's always theoretically guaranteed if there's just 2 observations too?
So even though I have time varying covariate, I need at least 3 observations in this case.
Okay. Okay.
Or maybe because it's binary, it's also binary. But anyway, you don't get any error term. You can't separate the error, right? Because I have 2 points and I'm connecting them. So I don't get any sense if I had a 3rd point, I might get some residual variation
Yeah.
that the procedure could distinguish between that and the between subject variation in the slopes. So I don't know. Let me show you how you do that. So this is how you add a random coefficient. You just say whatever you want to be the coefficient on to be random, and you give it the level. It defaults by always making an intercept. So the default is if I put a random coefficient, it's going to make a random intercept. So you have to add another command to take out that random intercept. That may work. I don't know for sure. In other words, it could be you can't distinguish the beta 0 variance of beta 1i and beta 0i and eij here. But if I took one of those betas out, maybe it would still work. I don't know. Worth a try.
Would you do minus and then parentheses 1 given ID to take out?
I think you have to put like a -1 ID, so you have to let it know. Don't automatically add the random intercept when I add a
Yeah.
random coefficient.
Yeah, exactly.
I haven't done it.
Okay.
It's worth doing. Again, you're not going to get good estimates of things anyway because you just don't have enough repeated measures. But all right, here's the more classic situation. Here's the more realistic situation. I'll go over this, and then we'll stop for the day. So this is the where we just have all the data. I'm not, we have observations measured at different times, viral load, and we're going to use baseline viral load here as an adjustment variable, right? And this allows us to distinguish what and what. It's just for history, so we get the difference between maybe longitudinal effects, how has it changed, CD4 change if you change the viral load within a person versus cross-sectional effects. Is there some bias that enters because we have characteristic individuals that are stable, but they confound viral load and they have arrows to viral load and CD4 count. So again, just a way to adjust for the history. And then I'm going to add random intercept. And again, this doesn't vary. It's constant within the subject, right? Because I keep beta 1i the same for every observation. So I can't look at the effect of beta 1i at the individual level. So I can't make a beta 1i. It won't work. I just leave it out. But this does vary within a person, so I could estimate the variance due to the fact that that longitudinal effect here can vary from person to person. They can have different slopes in how their change in viral load affects their change in CD4 count. That wasn't there. And again, this is more complicated because we had unbalanced data, right? So we actually get big, just looking at this one here, We get big differences between the estimates when you do exchangeable versus naive, right? Because we rate the data so differently from one to the other. These are very, very imbalanced, and it has high correlation. So it's going to downweight people with lots of observations if you use exchangeable relative to independence, and you get this thing that we've talked about quite a bit. Oh, this one, wait a minute. This one here, I'm only doing random intercept. Sorry, this is only random intercept. See, I only have this here. So this is like very much like the exchangeable. So it should look a lot like that, and it looks a lot like that. Not exactly. Again, it's not exactly the same estimate, but pretty close to naive exchangeable is what you'd expect. And obviously nothing at all like independence, because it uses that working correlation that's based, it's treated as the true correlation, but that working correlation is equivalent to exchangeable when it gets the weighted regression. So again, you're going to see this difference between assuming independence and assuming some dependence, like exchangeable, is going to change the estimates here, right? Because of that reweighting due to imbalanced data. Again, we have fairly high correlation. We think it's like 3/5, 0.6 or something like that. And again, remember last time that turns out this is our cross-sectional effect, looks kind of similar to our longitudinal effect, which implied that if I just took a random sample of subjects at different viral loads and didn't look at the change in viral load, I would get similar answers. So kind of interesting. Here. So this is when I add the beta 2i. So if I go no equivalent working correlation model in exchangeable for this one, right? Now this is a more complicated variance covariance model. It's all, the variance covariance is going to be a function of x now, of the actual change in viral load. At a particular observation, you can work it out, kind of similar to what I showed earlier when I added that one. So it's going to be more complicated. We may get something different from either from the GE now, because we have a different weight matrix and we have unbalanced data. So we might expect not exactly the same answers. Again, arbitrary correlation will assume between the intercept and that slope. And again, we can't estimate a beta 1 variance of beta 1i here because there's only one xi1 per person. We just keep it constant for the person. Okay, starting where I left off, and we'll go to the next lecture today about random effects mixed models. And you know, we've almost talked about everything universal about them. I think you learn more about them by just looking at the variety of ways you can use them and where idiosyncrasies can show up on occasion, things like that. So we'll talk about binary, and things are a little bit different when we do a logistic regression version of mixed model, but for the most part, its basic theme's the same. You know, you've got a model, you specify what you think is random with respect to the units you have, whether that's intercepts or actual coefficients when that's possible, and then you fit the models, and you get, again, the inference you get back by default is always what we would call naive. It's based on the model being true. And in this case, the model assumptions often they're not trivial model assumptions. As we've seen with the GE, when we compare different to naive to robust, we could see big differences there because the model is not in fact true. So these are fairly big assumptions, which is why in some ways fitting the biggest possible random effects model might be the most the most conservative thing to do, is to make sure you capture as much of the variability as exists, knowing that you can't fit everyone, and in many cases you're only limited to what it can be identified. And that identification part comes because it's oftentimes to separate out estimates of these things, these variance terms. Does it come from the intercept? Does it come from the residual error? Does it come from the coefficient? When you get more and more of random effects within the same unit, like the person level, it just can be hard to identify them with data you have. Many different values, combinations of them are consistent or give you the same likelihood. So anyway, we looked at this model. We were going through that sequence where we looked at simple 2 measurements per subject, fixed treatment, fixed covariate. Then we had 2 per subject where it varied within the subject, and now we're at the one where it's just more general. We have different numbers of measurements. I just wanted to point out again the importance of thinking about how to adjust for history, and in this case, we're doing this, but again, you don't have to use the first measurement of the covariate of interest. It could be other things you think might be better represent confounding. But this is the one advantage that longitudinal data really gives you, or one of the big advantages is that you're able to adjust for history, which means you can probably adjust for all the factors that are related for individuals, even if you didn't measure them, the ones that are stable, that don't change over time. But in actuality, we don't get a huge change. So a little difference in the standard error, which is interesting. This is going to be a bigger model, so more likely to be unbiased with regard to the variance model in this case. Bigger, so therefore less bias, could have more variability, which has other impacts. Again, all I have to do is put I want the coefficient for this to vary at the ID level, and it'll automatically add the intercept. And also this thing now, if I look at this has a different, that's the variability, that's a standard deviation in the impact of the change in viral load, right? If I believe this model, then the distribution of the slope of viral load versus the outcome, the standard deviation of that is 41.1. So kind of like, did I do this? I'll do it next time, but it sort of implies the distribution of the beta 1I looks like this. The center is at minus 54.15, and the standard deviation is 41.27. So that's what it implies about how the effect varies among the person. This is information that you get from mixed models that's different from G. You don't just get the estimate, you get what is the variability and the impact of viral load on CD4 count. And that can be pretty interesting. It gives you some idea of treatment heterogeneity that you get. And in this case, most people will have a negative effect, which is we expect as viral goes up, CD4, but it really can vary pretty dramatically over this. So, this is, I'll just say it's like minus 13, and this one is like, I'm sorry, minus 41 would be 94, like 13, minus 13. So that's roughly 75% of the data or so varies between minus 93 and minus 13. Anyway, I don't know if that important in this context, but it can be important. So that is one extra information that can be very useful, is when you have time varying covariates, you can get the variability and their impact, and maybe that has some policy implications, for what kind of people you would target to get an intervention or not, to reduce viral load in this case, et cetera. Yeah, and that's basically kind of the sequence that you do in practice. You choose a model of your fixed effects, and then you sort of try different random effect stuff, and you find what will work at all, and then we'll talk about next time, of the ones that work, how do we choose between them to get something that's closest to the truth? And there's a variant bias trade-off, right? I always get closer to less bias if I add more and more terms, but of course the variance starts exploding. So you want some balance of those two, and we'll talk about how to do that next time. Any last questions? Okay, we'll finish up this next time. Thank you. And then we just looked at how to do this. You'll have practice in lab today about how to implement these things and how to interpret the output. Again, it gives you estimates of the variance components, and it gives you estimates of the coefficients with, again, these standard errors are we would call naive. They're based on the model being true. It doesn't give you independence unless you have model that assumes independence, right? So it'll be based on whatever correlation model your random effects model implies. And then here, we'll talk about this more, but also you don't just get an estimate of the fixed effect, which is like the mean coefficient. When you have a associated random coefficient, you get the whole estimate of the distribution of the coefficients. Again, it's assume it's normal. So if you assume it's normal, all you need is the estimate of the mean one, which is the fixed effect, and then the variance, which are these variance terms. One last thing, if you have two coefficients like this, so they have a potential correlation with each other, then they'll come from a bivariate. In this case, there's two, a bivariate normal distribution, so not just independent normals. If you wanted to generate new values from that bivariate distribution, you would generate them from multivariate normal with a certain variance covariance matrix that you can also grab from the program. So it's just something to think about. Here, I'll do. So, this just points out that when you're looking at the coefficients, if that's your main thing of interest and you get your standard errors, particularly in a linear case, there's not really that difference in interpretation from GE. It's kind of the same. Again, you can interpret linear model, you can interpret the coefficients both as marginal effects, the ones you get from the GE, where you're not conditioning on the random effects, but also conditional ones. And you can see that simply from the math. If I look at a change of x of 1, and if I keep the random coefficients fixed, that is for the same person, that's like looking at the effect within a person. If I keep those fixed on both sides, it cancels out. But also if I don't do that, but I just take the mean of those random effects is 0. So I always will end up with, let's say, beta 1 on the fixed effect for either if I define my comparison of interest to be marginal, averaging over people, versus conditional, keeping the random effects fixed, and that's just because that in that linear model, those things cancel out. That's not true in the logistical case. So they have fundamentally different interpretations. Again, this is one of the virtues of these mixed models, is you get, when it's interesting, you get ideas about the relative contribution of the variance from different of these error terms. Whether the contribution of variance is from the residual in the linear case, is the within subject, let's say, variation the most important, whether it's the intercept, which is really more between person variance in their means, whether it comes from a particular coefficient on a covariate that's random, which suggests that variance comes from the fact that the effects can be different between people. So you get some idea of that variability, not just the estimate itself, which you only get from GE, right? You just get the estimate. You get confidence interval, that's sampling variability, but you don't get any measurement of its variability, true variability in the population, because that's not the term of interest. It's giving you essentially the average one. And the other thing that we'll do a little bit of is I can also get predictions of the intercepts for people. After I fit this model, I can say, well, I want to know what the intercept is for person 5, and you can retrieve that as well. And we'll have a short lecture on how that's done after you get the estimates of the variance terms and the coefficients. You can ask, okay, what's the best estimate of the random effect for this person given their data? So you can get predictions that are specific for the people in your data. Let's say I want to predict something in the future about them. I want to use their intercept and their, let's say, random slope as opposed to the average one. Yeah.
And are mixed models also useful for a population level inference?
Well, I'm just saying, can you be for both?
Can both, yeah.
Right. Well, let me just I should probably just do a simple example, right? So it's boring math, but you get the picture. So let's say I have a simple model, which is like, right? And again, this is random and this is random, right? We always treat the xij's, we're conditioning on them, which is the same as treating them as fixed. So we're not looking at their variability and its contribution. So in this case, if I'm going to say what is E, Yij, given xij is little x plus 1, but I also want to fix I'm going to say this is just for person I, particular person. So I'm going to keep their intercept fixed because it's for the same person. Minus e ij given xij equals little x. Again, fixing that one. The only thing that's random now is the error term. So if I take the expectation of this equation, let's just do the first one. So that'd be like, I'll do this one. That's e of beta 0I plus beta 1 xi, little x, sorry, little x plus 1 plus eij, right? Oh, and the beta 0 too, sorry. Beta 0 plus beta I. That's that one, right? And what's that equal to? Well, the expectation of a constant is a constant. This is also, I forgot to put something, sorry about that. This is conditional on beta 0I. I'm putting the x in there, so I don't have to condition that anymore. So this beta 0 plus beta 0I plus beta 1 x plus 1 plus 0, because the mean of that is 0. It's always assumed to be 0. Minus, this will be beta 0 plus beta 0I plus beta 1x plus 0. If I take the difference of those two, I'll get beta 1, right? So even though I fix this, I say I want the within person subject change in the mean. If I change xij by 1, those two cancel out. Now if I don't condition on that, so then I'm not conditioning again on this beta 0i, I'll also have to take the mean of that beta 0i term, and that's also 0. So it still cancels out in either way. This one is the subject-specific conditional effect. The other one's the marginal effect, but they're the same in this case. Again, if you do that in the logistic case, the math doesn't work out, not the same. Yeah.
And if we had a random slope here that was based on individual, and then we were trying to, like, say predict for somebody who we hadn't seen before, you just drop all the terms that are random for individual. Is that true? Or
Well, if I wanted the prediction for a particular individual that's in my data, I could use their beta 1i. But if I wanted to compare, if I also had a beta 1i and I wanted to compare one unit change in x, I would also keep beta 1i fixed. So I get the exact same thing. Yeah.
but with a new person who I say I've never seen before.
Well, then you're right. Then the prediction, you can't use their beta 0i, you haven't used it.
Yeah.
So you basically have to give them the average prediction, right? It would just be that you would predict beta 0 plus beta 1 xij. You wouldn't use a beta 0i, you don't have it.
Oh, that makes sense.
Yeah, so this would be for if you have a random intercept
Right.
in your model, right?
Yeah, exactly.
Okay.
Yeah.
Okay.
It's just for this specific model.
Yeah.
So anyway, that's often a big deal. It's made by mixed models in that they give you this kind of individual level estimate of the association because of this being able to fix on beta 0i. It just turns out mathematically in a linear case it's the same as the population level, which just means I'm comparing two groups of people that differ by xij equals 1. And I'm not conditioning on them having a particular beta 0i. So it's the same, you get the same number in this case. So again, what do you do if I have information not just on the estimate mean value of the coefficient, which is going to be beta 2 hat, but also it's the variance of the beta 2i in this case. Again, sigma squared 2 is defined to be the variance of beta 2i. How can I use that information? Well, it turns out I know that the estimated distribution is that it's normal. So and I'd estimate the mean to be the fixed effect. I don't know the true beta 2, but I would plug in the estimate of it, which is beta 2 hat. And that gives me a whole distribution of possible associations, in this case of how the change in viral load changes mean CD4 count. So you could look at how variable the impact is, and that can have some interesting, medical implications, public health implications, et cetera. So you get more information from a mixed model. Again, it's information based on making fairly strong assumptions, but it does allow you then to look at variability of impacts of coefficients. I mean, this mainly makes sense when I have a random coefficient on a explanatory variable. A random intercept, is really just a random mean difference when x is 0. But these are really associations, right? The betas that are multiplied by the x's are associations. So you get the actual variance, variability in the association. In fact, you get the whole distribution by assumption and estimates of both the beta 2 hat and the sigma squared. So again, I could take the estimates I get back of sigma squared hat, and I could get the estimates of beta 2 hat, and I could draw the whole normal distribution of the estimated beta 2i's, right? And again, the effect in this case, the slope for a person, I in this case, is beta 2 plus beta 2i, right? It's the mean one plus the departure of that person from the mean. That's how it's parameterized in the model. So you don't just look at the beta 2 always has by assumption, beta 2i always has mean 0. If I want the actual distribution of the coefficient, I have to add beta 2 to it because it's the difference between the mean and the person i's particular value. This is just taking that results and drawing it, right? So here's a 0. This is no association. And you can see predominantly by this estimate, most people would have a estimated slope that's less than 0, which you expect, right? Because CD4, as viral load goes up, you expect CD4 count to go down. So the association would be a priori, you expect it to be negative. And you can say things might be interesting, like what proportion of people have this kind of effect? That could be interesting. What kind of people, if I'm looking at treatment effect, for instance, what kind of people have a treatment effect that's particularly effective, and which kind of people have an effect which is, in this case, is actually positive. Now, I don't know if do you really believe that? I don't know. It's a normal assumptions it's putting in. So again, if the true distribution of people's responses of change in viral load adjusted for baseline viral load is probably not normal. It's the only assumption you can make in order to get identification of these parameters. So again, you have to be a little cautious about taking these normal distributions too seriously. They're not really checkable with the data. They're just by assumption. Yeah.
Alonso, did you say that beta 2i has mean 0, or is?
No, this is wrong.
Beta 2i
It should be.
is it plus beta 2?
Yeah.
Is it? Okay.
I'm sorry, this is wrong.
Okay, that makes sense.
That's what it should be. I'll put beta 2 star,
Okay. Nice.
which is going to be the actual coefficient for a person.
Because the mean on that distribution is just beta 2.
Right, and the mean of the error terms or the random effects is always 0.
Yeah.
Okay, so this one important topic that I don't give a lot of airtime to, it's actually fairly simple to do. I mean, there's certainly debates whether it always works or not, is to use model fit statistics to choose your random effects model. So the way it usually works, it's recommended is you have your fixed effects part. What covariates are you going to add, right, with the fixed effects coefficients? And then maybe you come up with a sequence of different random effects models. You had a random coefficient here, a random intercept here. Maybe you have different levels. It's not just person and time within person, but you could have household in person and time within person. So you can have random effects at different levels. And then every time you add those, they add more parameters, right? So every time you add more random effects, it adds variance terms and covariance terms. So the data becomes more flexible, the model. So it should be able to capture the truth more flexibly. But of course, it's also going to add variability because the more parameters, the more and the data staying the same, the more variability typically you're going to estimate those parameters with. Their sampling distribution gets wider. So it's this variance bias trade-off. The more I add the complexity in general, the less bias you have because you're able to capture any arbitrary correlation pattern if I make it more and more complicated. But the more variance you're going to have. So less bias and the more variance, and typically you want to balance those. You want to you don't just want to minimize variance because I can do that by saying the answer is 7. That's perfect. Variance is 0. But you also don't necessarily want to have minimum bias because you can have to have huge cost of variance to make sure your bias is really small. I'm making really overfit models with way too many parameters for your data to be able to estimate well. So there's ways of balancing this variance bias trade-off. I mean, usually you think what you really want is the mean squared error to be. So that's variance is bias squared. So it's like if I increase one, I decrease the other, and vice versa. And you want to balance those two. That's usually the optimal goal, is to balance the variance and the bias. I mean, typically, it depends on what you're estimating. Because this is often done with regard to prediction, is the way this is decided. But I really, it doesn't tell you necessarily the best thing to do for estimating a particular coefficient would be to make a more complex model, even if prediction says you should make a more complex model. And that's a subtle difference, and it's really only been, I think, a fair amount of research more recently in how to properly overfit models if their thing of interest isn't the whole regression function, but just a part of it. But in general, we're not worrying about that in this class. We're just going to say we'll use the prediction, the likelihood, and we'll use that to guide whether or not we think a model relative fit of these models. And the way that's done, and it's only not ad hoc when you have nested models and you're doing maximum likelihood estimation, is a Cocky's information criteria. And when it does, if it takes 2 times don't worry about the 2. 2 times the negative likelihood. So the log likelihood is always negative. I mean, if your outcome is binary, for instance, if it's not density, you can get other things. But let's assume that we have a discrete outcome. So it's always going to be negative because it's just a product of probabilities. If I take the log of a product of probability, a product of probabilities always between 0 and 1. If I take the log, it'll always be negative, natural log. So the bigger this term here is, the bigger the worse. The bigger it is, the more negative the log, which means the smaller the likelihood, which means it's not fitting as well, right? And as well, this is the penalty term. So this is the number of parameters that you have. And so I know when I fit more parameters, the likelihood will always get bigger. So the log likelihood will always get less negative. Doesn't matter even if I'm fitting parameters that have no additional fit. That'll always happen because it'll always be able to bend a little bit to the data. And you want to make sure that the likelihood is increasing enough, or the log likelihood is becoming less negative, enough to make the additional parameters worthwhile. And this is a way to balance variance and bias. So this is sort of the bias term. That's kind of the variance term, very roughly. And you're trying to sort of optimize these two. And so it works okay. It's not the optimal way to do this. The optimal would be what's called likelihood-based cross-validation, where you would take part of your sample, divide it up, and let's say, just make it easy, 2 equal halves. You would fit the model on one half, and then you'd get the likelihood on the left-out half based on that fit, and you switch roles, and then for each of those splits, you would fit a bunch of different models, and you choose the one that had the best overall cross-validated likelihood. That's kind of, you can base that on first principles. You can come up with a theory that says that will always do best with regard to whatever loss function. In this case, our loss function has to do with the likelihood. This is sort of, I think of it as a shorthand, low computational burden way of trying to do that exercise. That tends to work pretty well in practice often. So, and there's lots of rules of thumb. Like if your AIC doesn't change by at least 2 comparing 2 models, then you consider them kind of the same. There's no difference in the fit. Lots of rules of thumb for these things, which are somewhat arbitrary. So you do this for a bunch of different again, you're keeping the coefficients and the covariates you're putting in them all fixed. You're just changing different random effects parts, and you choose the one that gives you the smallest AIC, smallest is best fit. So that's one suggestion you can do. It's not crazy. So that's a reasonable suggestion that tries to get something that's at least closer to getting an estimate of the true covariability of everything in your data without overdoing it, because you just don't have the data to do something that's completely non-parametric. In your case, you can just think smaller AIC, the better. So again, if I have two models where I increase the number of variance terms, so P gets bar, but the likelihood doesn't change much, you're not going to favor those, right? Because they're going to be worse than the model with fewer parameters, since adding those didn't change the likelihood at all. Didn't make it much better, if at all. So now I'm just comparing these two. We had a simple random effects model where we just had a random intercept. Then we had the random coefficients model where we added both the random intercept and a random slope. Again, the fixed effects parts are the same. If I took off all the error terms, it would look exactly the same. And then I do this. You get things I haven't talked about too much, but I went a little bit. The interclass correlation coefficient, where that's relevant, and that's in the simple random effects case, where you just have a random intercept. That's the variance of the random intercept over the total variance. And you also get the AIC, right? And the other thing you can do is like compare. Does it really matter? If I only care about like this thing right here, obviously. In this case, I added robust. So in this case, I think it's in the code. I showed how to get a robust estimate of the standard error, even though I'm fitting a mixed model. So we could compare it, in this case, like we do in GEE. You can see this is pretty far away from each other, so kind of it suggests that the simple random effects model is not a great fit in this case, because the standard errors change. And then if I fit a random coefficients model, I see they're very similar, which suggests that this is getting closer to the truth, maybe, or getting at least closer than the previous model. If I looked at only the robust, it's kind of like we see with GEE. They're both the same, so they're not really changing how the data is reweighted in any way, even though it has the same principle here. It's unbalanced data. A new implied correlation structure should give you different estimates, but actually those estimates are pretty similar. And if I use the robust here, it wouldn't matter what I chose, right? It's not really, no, it does matter quite a bit. No, it doesn't. No, they're both 50, they're close to the same, 50. If that's the coefficient I really care about, that change in viral load and how it changes CD4 count, they're about the same. And if I use robust, I get about the same answer, but you can see I really wouldn't get the same answer if I use the standard when you get back, which is the naive. So it does show you, in this case, you want to choose the bigger model for sure. If I wasn't going to use robust, I happen to know it now, but you don't always know it. And if you check it, it's consistent. Look at the AIC is smaller for this model by, several hundred. So that's certainly significantly a better fit. And therefore, you would go with the random coefficients model. Again, it shows you kind of the power of just fitting the robust standard even beyond mixed models, is that it gets rid of some of this decision making. In this case, if I did that, it wouldn't matter what I fed anymore. It's not going to matter. So again, you always want to evaluate these models in the context of what you're estimating, right? So if I only cared about beta 2, the choice, and I'm going to use robust standard errors, choice isn't that important. I get about the exact same inference. It's what it matters is really when the inference changes about your particular parameter of interest. But all things being equal, this is a better fit. And again, you typically don't see this. That's as a special overlay you have to add to mixed models to get the robust. So it just shows that it's probably a worthwhile thing to do, because again, it's only a limited number of potential covariance models that you can add with mixed models, and maybe it's just not good enough. And so you always want to go for robust at the end. Okay. That's that's it for this lecture. Any questions about this particular thing? We're going to continue on with this, linear models in a second. Just go in a little more detail about another model. But this is basically the idea. Now, there's other things we could talk about, and we will talk about in the future, like prediction, whether you're predicting in sample or out of sample, maybe some more sophisticated use of the actual variance terms, things like that. But this is the basic structure. You know, you've got your fixed effect model. You're going to fit based on whatever a priori information you have, or maybe use some empirical work to try to decide on that. You have a set of potential random effects models you could fit. Some of those are going to be guided by first principles, like I really think the intercepts will vary, or these people should have differences in the impact of this, and I want that to be modeled because I want to see the estimates of it. But if you just don't really, that's not really driving you, you just want to estimate the coefficient that's the bet as good as possible, that's a different thing. So you do these fits, you compare AICs, you see whether it makes a difference in the end, so you know what decision is important and what decision is not. If you do have a decision that really changes your inference, you want to understand why that's happening. That's kind of generally my approach to these types of things. You know, you want to overfit too much, but in this case, the part of interest I'm consuming in this case is just the beta 2. That's the measure of association I care about. And so in this case, these are all kind of second order type of considerations to make sure I get the inference right and that kind of stuff. So in this case, I could report either one as long as I did the robust standard error. If I'm not going to do the robust, I would do the random coefficients because it's a better fit to the data. That's how I would approach that. Okay.